All right, everyone, get ready for a serious brain workout because today we're diving deep, and I mean deep, into the world of cells and atoms.
Yeah, we're talking microscopic level here, the fundamental building blocks of life.
And to guide us through this tiny but totally mind-blowing universe, we've got two awesome sources.
First up, we've got the Amoeba Sisters, those YouTube legends who are going to give us a super fun and surprisingly informative tour of the cell.
And then we'll switch gears and get a bit more technical with a college lecture by the one and only Jim Hutchkins, who's going to break down the atom for us.
So we're going from a super fun animated world to a, well, maybe slightly less animated lecture hall.
But trust me, both are going to be packed with incredible insights that'll make you see the world in a whole new way.
Absolutely. The goal here is to connect the dots between these two seemingly separate worlds, the cells that make up living organisms and the atoms that make up, well, everything.
It's like, whoa, we're all just made of this tiny stuff. It's incredible.
And what's even more amazing is that by understanding these microscopic building blocks, we can actually explain some pretty big real-world phenomena.
Things like, why does bleach kill bacteria?
Or what's really happening at the molecular level when you get a sunburn.
It all boils down to chemistry, those fascinating interactions between atoms and molecules that make life and, well, everything else possible.
Exactly.
So let's start with the Amoeba sisters and their super fun, super creative take on the cell.
They compare a cell to a bustling city, which is a perfect analogy, honestly.
It really is. They even have this quirky rating system for the different parts of a cell, the organelles, like they're judging a reality TV show.
Yeah, it's pretty hilarious. So, for example, the chloroplast, the organelle responsible for photosynthesis in plants, gets a 10 out of 10 rating from the Amoeba Sisters. They call it a total cinnamon roll, which I just love.
I know, right? It's like the sweet little baker of the cell, whipping up sugar from sunlight. It's so cute.
But then there's the lysosome, which is responsible for breaking down cellular waste. And it also gets a 10 out of 10 rating,
For being a total badass, they call it a wrecking ball and an enzyme grenade.
which, fair enough, is a pretty intense organelle.
So we've got the sweet cinnamon roll chloroplast and the badass wrecking ball lysosome.
And this contrast in their favorites really highlights the diversity of functions that these organelles have.
Yeah, and it emphasizes how even at this microscopic level, life relies on balance. Creation and destruction, energy production, and waste removal.
It's all connected.
And this city analogy is so helpful because it really shows how if one part of the cell malfunctions, the whole thing can go haywire.
Exactly. Just like if the power goes out in a city, things get chaotic fast.
Imagine if the garbage trucks stopped working. Total disaster.
Right. Or if the transportation system breaks down, nothing can get where it needs to go.
And that's why understanding how these organelles work and how they interact with each other is so crucial to understanding health and disease.
Absolutely. If the mitochondria, for example, those powerhouses of the cell, aren't working properly, it can lead to some serious health problems.
Like mitochondrial disorders.
Exactly. And scientists are actually studying these organelles, these tiny little power plants, to develop new treatments for these conditions.
It's like microscopic mechanics working on the engines of life. Pretty cool.
Now, let's shift gears a bit and zoom in even further, past the organelles to the atoms that make up everything, even those hardworking mitochondria.
Okay, we're going subatomic.
In his lecture, Jim Hutchkins introduces us to two main models for understanding atoms,
There's the electron shell model.
and the orbital model.
So two different ways of visualizing the same thing.
It's like, think of it like Google Maps versus a hand-drawn map.
Both can get you to your destination, but they show you different levels of detail.
Exactly. Now, before we dive into those models, let's talk about the three main subatomic particles that make up an atom.
Okay, the building blocks of the building blocks.
We've got neutrons
Protons.
and electrons.
So where do these tiny particles hang out?
Neutrons and protons, they're buddies. They hang out together in the nucleus, the atom's core.
Okay, so they're like the dense part of the atom, like the pit of a peach.
Yeah, a good way to think about it. And these guys, they give the atom its mass.
Muscle of the atom.
But the real stars of the show, the ones driving all the action, are the electrons.
Ah, the electrons. Tiny but mighty.
They're super tiny, negatively charged, and they whiz around the nucleus in these specific zones.
Okay, so those tiny little electrons are the ones calling the shots. What makes them so important?
Well, they determine an atom's chemical personality, how it interacts with other atoms.
Like its social skills.
Exactly. Whether it's clingy or standoffish, whether it forms bonds easily or plays hard to get, they basically orchestrate the whole dance of chemistry.
Wow, so electrons are like the social butterflies of the atomic world. Interesting. But this isn't just some abstract science stuff, right? Understanding electrons helps us understand things in our everyday lives.
Absolutely. Think about bleach, for example. It's a powerful disinfectant because it can steal electrons from bacteria.
Like an electron thief.
Exactly, basically disrupting their ability to function.
That's hardcore. I never realized bleach was such a ruthless electron snatcher.
And this is just one example. Understanding electron behavior helps us explain all sorts of phenomena, from how batteries work to why certain materials conduct electricity.
So we're talking about tiny particles leading to big, real-world effects. I'm definitely starting to see those connections.
And we're just getting started. Next up, we'll delve deeper into the world of isotopes and the periodic table.
Tools that help us make sense of this incredible diversity of atoms and how they behave. I'm ready for more.
So we've been talking about electrons, these tiny particles zipping around the atom's nucleus.
Yeah, those electron things sound pretty important.
They really are. And here's the thing, not all electrons are created equal. The ones that really matter for bonding, for how atoms connect with each other, are called valence electrons.
Valence electrons, okay, remind me, those are the ones on the outer shell of the atom, right?
Exactly. They're the ones on the outermost energy level. So you can think of them like the atom's social butterflies. They're the ones interacting with the outside world, making connections.
So if electrons determine an atom's, personality, then valence electrons are like its dating profile. They determine who the atom wants to hook up with.
That's a great analogy. And just like some people are more outgoing, make friends easily, some atoms, based on their valence electrons, are more likely to bond with others.
Makes sense. But why are some atoms so eager to bond in the first place? What's in it for them?
Stability. Atoms crave a sense of balance, and that means having a full outer shell of valence electrons. You could say they want to achieve electron nirvana, where everything is balanced and harmonious.
Electron nirvana. Okay, I like that. But how do they achieve it?
Well, they can do it by sharing electrons with other atoms to form what we call covalent bonds. It's kind of like a chemical roommate situation where they're both contributing to a full electron pantry.
Sharing is caring.
Right. Or they can completely gain or lose electrons to form ionic bonds, which is more like a hostile takeover, where one atom steals an electron from another to complete its own shell.
Whoa, so atoms are willing to go to war over electron. That's dedication to electron nirvana.
It is, and this electron tug of war, it's what drives so many chemical reactions. Remember chlorine, the electron snatcher we talked about
Oh
earlier?
yeah, the bleach bandit.
It's so good at grabbing electrons because it's just one electron away from achieving a full outer shell, reaching that state of electron bliss.
So chlorine's like an electron addict, always looking for that next fix to complete its collection.
You could say that, and that's why it's such a powerful disinfectant. It disrupts the electron balance of bacteria, basically messes up their whole chemical system.
Okay, that's pretty wild. So what about those atoms that are already at electron nirvana? Those noble gases Jim Hutchins mentioned, like helium, neon.
Ah, yes, the noble gases.
They already have a full outer shell, so they don't really need to bond with anyone else, right?
Exactly. They're like the introverts of the periodic table. They're content with their electron arrangement, don't feel the need to mingle.
So they're like the cool kids who are already part of the in crowd. They don't need to impress anyone else.
Pretty much. They're what we call chemically inert, meaning they don't readily react with other elements. They're happy just floating around, minding their own business.
Makes sense. Now let's talk about the periodic table. Jim Hutchins called it a chemist's best friend, but to be honest, it's always looked kind of intimidating to me. Like, how do you even make sense of all those squares and numbers and symbols?
I get it. It can seem overwhelming, but the periodic table is actually an incredibly useful tool. It's like a giant map that arranges all the known elements based on their atomic number and chemical properties.
Okay, atomic number, that's the number of protons in an atom's nucleus, right?
Right? It's like the element's ID number. And the genius of the periodic table is that it groups elements with similar properties together in columns. We call them groups. So you can see trends, predict how elements will behave based on where they sit on the table.
So it's like a cheat sheet for understanding how atoms interact.
Exactly. Take those alkali metals we talked about earlier, lithium, sodium, potassium. They're all in the first column of the periodic table, group 1, and they all have one lonely valence electron that they're desperate to get rid of.
And that's why they're so reactive. They're like throwing that electron at anyone who comes clear. Please take it. I need to achieve electron nirvana.
That's a great way to think about it. And because they're so eager to lose that electron, they react pretty violently with water, producing hydrogen gas and a lot of heat.
Okay, that's why you shouldn't throw a chunk of sodium in the bathtub. So the periodic table can actually help you predict which elements are going to be the drama queens of the chemical world.
Absolutely. It's a powerful tool for understanding the patterns and trends in chemistry. But remember, it's not just about memorizing the table. It's about understanding the underlying principles, those fundamental concepts that govern how atoms behave.
Okay, so the periodic table is like a map, but you need to know how to read it to find the real treasure.
Well said. Now let's shift gears a bit and talk about what happens when these atoms come together to form molecules. It's not always a peaceful coexistence.
All right, I like where this is going. Atomic drama, tell me more.
Yeah, it's like the atomic world has its own set of rules for engagement, you know? Attractions, repulsions, energy exchanges, and those crazy electrons always stirring things up.
Sounds like a wild party down there at the atomic level. So how do we even begin to make sense of all this?
Well, chemists use what we call chemical equations to describe what happens in a reaction. It's kind of like a shorthand for showing which atoms are involved, how they rearrange themselves to form new molecules.
Okay, so it's like a before and after picture for atoms.
Exactly. You can see who started the party and who ended up together at the end.
I like that.
And just like a recipe needs to be balanced, the right proportions of ingredients, a chemical equation needs to be balanced too. You can't just poof, create or destroy atoms out of thin air. Gotta count for every single one.
Right, no atomic magic tricks allowed.
Exactly.
But what about those reactions that seem to go in both directions? Jim Hutchkins mentioned reversible reactions. Is it like the atoms can't make up their minds about who they want to be with?
That's a great way to think about it. In reversible reactions, the products, what you get at the end, can actually turn back into the reactants, what you started with. It's like a chemical dance where the partners keep switching back and forth, depends on the conditions.
Okay, so like a chemical tango. Sometimes you're leading, sometimes you're following.
Exactly.
So what determines which way the reaction goes?
Well, one factor is concentration, how much of each reactant and product is present. It's kind of like a popularity contest. The side with more votes, more molecules tends to win out.
Chemical democracy. Majority rules.
Pretty much. Another factor is temperature. Heating things up usually speeds up a reaction because the molecules have more energy to move around, bump into each other.
Turn up the heat on the dance floor. More collisions, more drama.
Right, but sometimes you need more than just heat to get things going. Jim Hutchkins mentioned catalysts.
Oh yeah, catalysts. What were those again?
So those are like the matchmakers of the chemical world. They speed up reactions without actually participating in them, like that friend who sets you up on a blind date but doesn't stick around to watch the awkwardness unfold.
I love that analogy. So catalysts are like the wingmen of the atomic world.
Exactly, and they're incredibly important in biological systems. Enzymes, for example, are biological catalysts that speed up all sorts of biochemical reactions in our bodies.
Like digestion, DNA replication.
Exactly. Without enzymes, those processes would happen way too slowly to sustain life.
Wow, so catalysts are like the ultimate multitaskers, making things happen without getting their hands dirty. Impressive. Okay, I want to switch gears for a second and talk about the different states of matter. Solids, liquids, gases.
Sure.
It's amazing how the same substance, like water, can exist in all these different forms. What's the deal with that?
It all comes down to how the atoms and molecules are arranged, how much they're moving around. In a solid, the molecules are tightly packed, vibrating in place like a very well-organized marching band.
So solids are all about discipline, order, no room for freestyle.
Right. Then in a liquid, the molecules are more loosely arranged. They can flow past each other, kind of like a crowd of people mingling at a party.
Liquids are more free-spirited.
Exactly. And then a gas, the molecules are far apart, zipping around randomly like kids running wild in a playground.
Okay, gases are the party animals, no boundaries.
That's a great way to put it. And the transitions between these states, they're fascinating too. Think about ice melting into water or water boiling into steam. It's all about adding or removing energy to change how those molecules are interacting.
Okay, I'm kind of seeing it like a choreographed dance routine, but instead of dancers, we've got molecules changing formation.
I like that. Now let's talk about solutions for a minute. How you dissolve sugar in water to make lemonade.
Oh yeah, lemonade the best. But what's really going on at the atomic level when that sugar disappears into the water?
So in a solution, the solute, in this case the sugar, it breaks down into individual molecules that get evenly distributed throughout the solvent, which is the water.
Okay, so it's like the sugar molecules are getting a VIP pass to the water party. They get to mingle with all the water molecules.
Exactly, and this even distribution, that's what makes a solution different from a suspension, where the particles are larger and eventually settle out over time. Like muddy water, the dirt particles eventually sink to the bottom.
So a solution's like a perfectly blended smoothie, and a suspension is more like a chunky soup.
That's a great analogy, and this concept of solutions is crucial in biology. Our blood, for example, is a complex solution of water, salts, proteins, all sorts of molecules.
Wow, we're like walking, talking solutions.
It is pretty amazing, and it all comes back to those tiny atoms and their incredible ability to interact and create the complexity we see in the world around us.
I'm starting to see the world in a whole new light, like a giant chemistry set where everything is made of these tiny building blocks, constantly interacting, reacting. It's pretty mind-blowing.
It is, and the best part is we've only just scratched the surface. There's so much more to explore, from the intricacies of organic molecules to the amazing diversity of chemical reactions that drive life itself.
Well, I don't know about you, but my brain is definitely buzzing. Huge thanks to the Amoeba Sisters for their wacky cell tour and to Jim Hutchkins for his deep dive into the atom. I feel like I just got a crash course in the building blocks of life, and I am here for it.
Absolutely. And to all of you listeners out there, keep those brains buzzing, stay curious, and never stop exploring the world around you.
We'll catch you on our next deep dive. 5-2.